Okay, so well, first let me thank the organizer for having me here and for giving me the opportunity to talk. So indeed, I will bring the discussion towards something more formal, but perhaps still a little bit in the theme of today's session, in the sense that it will be a little bit exotic. And it will connect in some way also to Flux Tube via duality with string theory that I will recall and explain. So what I want to mostly talk about is the behavior of gluon scattering amplitude in planar n equals 4 superior means, which is, as you all know, a sort of laboratory for theorists to explore mathematical and physical properties of complicated observable like gluon amplitudes. And what I'm going to say today is based on some work that we published with Lance, Dixon, Georgios Papatanasiou 2 years ago, and also some work in progress with Lance and Yorgos and with Andy Liu. Okay, so let me start with a very basic think about scattering amplitude. So of course these are textbook observables, so they don't need like much introduction, but they are observable in a particular way in the case at hand because they are not really measurable. Well, first, the theory I'm going to talk about is not a real theory, so there is nothing to measure. But on top of that, we have infrared divergences in this theory, which means that whenever we want to talk about this theory, we always have to think about switching on some regulator, and also possibly if we want to get something physical out of it, like remove the divergences, integrate them properly, like we do, for instance, to calculate cross-section or other physical quantities. So they are not observable, but they are definitely central, and they carry a lot of information and a lot of useful, I would say, physical information in the sense that they deal with potential quantities. So they what they do very well in general is to reveal symmetries of the theory. In particular, the symmetries that are not visible in, for instance, Lagrangian description or other approach. And on top of that, the higher divergences are also of great interest in that they carry information about physical states. And in the case at hand, in the case of gluon scattering amplitude, it is well known that these infrared divergences are controlled by cusp light-like Wilson line. So the idea here is that the divergences come from the IR, so from long distances, and that by emitting some low energy gluons, and that in this approximation, the particles that are flying away, the gluons, do not just travel at the speed of light without much recall, and so behave essentially like sources, classical sources, like in the Wilson line setup. So the claim is that the divergences that we are dealing with here, especially in the planar limit, are very well understood, and they can be mapped to the divergences of a cusp Wilson loop, which is very well known to be controlled by a single number, which is a cusp anomalous dimension, and which is in this theory only a function of the Toth coupling in the planar limit, for instance. It gets multiplied by something that you may think of as being some sort of area. It is integral over the light cone coordinate on the two segments here, the U and V light cone coordinate of, say, the propagator, the gluon propagator. Okay. Of course, it's not an area in physical units. It's more like a doubly logarithmic area. So it's an area in a sort of conformal sense. And but it becomes an area if we think in terms of a dual description, in terms of the dual string. So because of all of that, the cusp anomalous dimension can also be thought of as measuring or giving us the energy or the density of energy of the chromolectric flux for a pair of quarks, I mean a quark-antiquark pair, which are just moving at the speed of light. So this is how flux tube appear in this story through this quantity that is characterizing the energy. But so this statement, I mean, this result is some old result that were obtained by particularly Gregory Gorchemsky and Radyushkin many years ago, and it is valid in general, for instance, in QCD, in general gauge theory. But What happens in planar n equals to 4 supernomials is that it gets promoted to something that is even more constraining and powerful, which is an exact relation between scattering amplitude and light-like Wilson loops. So the statement is that the log of the amplitude is equal to the log of the Wilson loop up to correction, which are essentially small when we remove the IR regulators. And with the mapping, sending the gluon momenta on one side of the duality to the light-like edges, or to I mean, what is making the polygonal contour of the Wilson loop on the other side. So the mapping of divergences again is kind of general here. In the planar limit, but what is non-trivial is that also the finite part. So what you may want to calculate, once you've understood the IR divergences of gluon amplitude, can also be extracted from the Wilson loop, or can be seen as defining a properly regularized Wilson loop. And this is endowing scattering amplitude or Wilson loop with dual form of symmetry, because this mapping is non-trivial at the level of the action of the generator of the conformal group. It's essentially making a double copy of the conformal group, which form what is sometimes called a Youngian symmetry, and which is a manifestation of integrability. So what it means in practice is that there is great hope that we can go very far with this type of constraint and possibly determine gluon amplitude or Wilson loop to very high accuracy. In practice, it's also a very powerful constraint in that, for instance, it is entirely fixing the 4 and 5 gluon amplitudes. One can write so-called conformal wall identity for the Wilson loop, which will only admit a single solution, which is given by the BDS ansatz in the case of the 4 and 5 gluons, which means that this amplitude, which are in other theory rather complicated and highly non-trivial, are here just entirely known, and again, essentially exhausted by the knowledge of the first anomalous dimension. So things get more interesting as we go to higher points, and the first non-trivial amplitude will be the 6 gluon amplitude in this theory, and it will still have a piece which is given by this Bern-Dixon-Smirnov ansatz that will capture the IR divergences and also a little bit of finite part entirely. But it will also receive a correction which is called remainder function, and that will depend as a consequence of the dual conformal symmetry only on the cross ratios. So it will not be a function of Mandelstam invariant, but of certain ratio of product of Mandelstam invariant, which are just the cross ratio of the Wilson loop. So I mean, again, you define in the usual way, starting from the distances between the cusps. So this is the first constraint, and this is a rather powerful constraint, as we will recall later on. But before going on, I wanted to, since I mean it is a workshop of a flux tube, I wanted to make perhaps the connection a little bit clearer with the type of flux tube that we have in this story, and they are not flux tube again living in the original theories. They are flux tube in the dual theory when we switch to the string dual description in terms of string theory in ADS, as we were taught many years ago. And there, when one tried to calculate gluon amplitude by, say, defining some gluon at the horizon of ADS in the IR, one finds that it can be mapped to a Wilson loop, which is at the boundary of the space, so on the other side of the space. So the surfaces are related by T-duality, which is some complicated map, some non-local map at the level of the worldsheet theory. They are rather different, but nonetheless, because of T-duality property or invariance of the action, they must give rise to the same area. So the two objects are different, but as far as the area is concerned, which is what we need to know to calculate the amplitude, they are just equivalent. And one thing that we may also learn rather quickly by then studying the property of this minimal surface in areas that are ending on the contour of the Wilson loop, which is a prescription for calculating the object in this theory, in the string theory, is, for instance, that the induced metric close to every corner is flat, and because the boundary is at infinity, this is how we develop divergences. So divergences really come from the fact that we have some flat worldsheet with a flat induced metric which has an infinite volume. Okay, so it's really like in this space, in this picture, it's really the same thing as an area law, and which is controlled by the string tension. Okay, which ends up being the same as a corresponding homologous dimension. What we get on top of that is the fact that the theory is on this non-cusp is extremely well understood. It has been studied through many loops by some people like Arkady and so on. And it is known to be integrable. In fact, through integrability, which is also, I mean, a set of method and also conjecture, almost everything is virtually known about the spectrum and the S matrix of this flux tube. So unlike some of the flux tube we heard about in the previous days, where integrability is essentially an approximation to understand some universal behavior in some large volume limit. Here, integrability is exact, and so in principle, give us access to full information. And indeed, it may be used to develop a systematic approach to the calculation of scattering amplitude at finite coupling, as was first pointed out by Aldai, Garuto, Maldacena, Sever, and Vier. But okay, getting back to the main thread of this talk, so I wanted to also recall that this duality at the basis is really at the bottom of many of the recent development in scattering amplitude, which take many different forms. I'm listing here a few of them, from some Grassmannian construction of the scattering amplitude integrand and associated amplitude hadron, if you've heard about that. To the amplitude function bootstrap program, which is led by Lance and his collaborator, and which aim at constructing scattering amplitude without either considering any Feynman integrals, and essentially by using the analytic property of the amplitude alone. So it's really a bootstrap in this sense, that you only use information that you want to be there, and find a bit miraculously that it is enough to pin down the object you want to construct, to more sophisticated techniques like the TBA and strong coupling, or the Pentagon OPE, or the BFKL approach that relies on integrability. And it has led to unprecedented results for perturbative amplitude. Well, first of all, for 4 and 5 points, they are known to all loops through this duality. So it's already a great achievement. And for the higher amplitude, where there is something non-trivial, some non-trivial function of the cross ratio to calculate, they have been obtained through this technique to very high loop order. 7 loops, for instance, for 6 point, 4 loops for 7 point, and so on. So that's really a lot of information, a lot of data to play with and to explore new kinematical regime of amplitude, and also possibly unveil new structure that could be inspiring, possibly for and applicable in other theories, or may also possibly help developing new approach to scattering amplitude that will enrich the list of techniques that we have. So the great hope that I've mentioned briefly earlier is the hope that one day possibly we could solve for a scattering amplitude, or maybe all of them, at a generic coupling in the planar limit and for generic kinematics. So nobody knows what it's going to look like, nobody knows how to write it down, but we already have many handles on it, and there is a hope that hopefully one day we will get some description of this type. But today we're still relatively far from it, and resumming the perturbative series, resumming all these loops, extrapolating them and resumming them, or resumming the kinematical expansions that underlie the non-perturbative approach like the Pentagon OPE, is still extremely challenging. Okay, so there is still a long way to go before we can, I don't know, write some sort of final answer, if anything like that exists. But a possible pathway here will be to start by having some scattering amplitude under control in some kinematical domain of interest, and in particular at the boundary of the kinematical domain, where it is expected to develop singularity. So singularities are often very interesting physically, they're also important when we start bootstrapping and so on, to it's important to know why exactly we expect to have singularities and of which type. And this is also where usually integrability proves to be extremely useful and powerful. As an example, this the flux tube OP Pentagon OP that I briefly mentioned is a way to systematically construct amplitude at finite coupling in the collinear limit. And there are also some variation around this idea that give us access to some partial resummation of this OP series, which is really rather complicated in general. And the Regge limit and the BF-Cal approach is yet another example of a regime where we can we can make progress using integrability. So the limit I want to talk about today are what we call origins, and they are sort of new limits in the sense that they haven't been so much discussed in the past, where important simplification occur and where there is hope that integrability is called to play a very important role in determining, in fixing the final answer completely. And roughly speaking,
Benjamin, just to let you know, you're at 16 minutes now.
Okay, thanks a lot. So this is a limit where a large number of cross ratio or managed time invariant, if you prefer, are sent to zero simultaneously. And what has been observed is that amplitudes develop large logarithm in this regime, a little bit like when we have higher divergences, we get logarithms that exponentiate. And which are controlled by just a few coefficients, which are constant, which are function of the coupling constant. And our goal was to this discussion, I will report on our exploration of this intriguing behavior at any coupling and for any gluons, and discuss the structure that is emerging. But it was first observed for the 6 gluon amplitudes by Lance and collaborators, that the log of the amplitude in the limit where the free cross ratio that parameterize the Wilson loop are sent to zero is quadratic in the logarithm. So in this limit, and because of symmetry, there is only 2 possible logarithms we can write, which are cyclic symmetric. And what has been observed through a relatively high loop order, 7 loop in the case at hand, is that the amplitude is just a simple function of these 2 quadratic log, double log, with coefficients which are a function of the coupling and which can be calculated again through 7 loop. It has also been observed to hold a strong coupling many years ago, but okay, the conjecture that it holds at any coupling were put forward only recently. And the structure and also the coefficient that we find are extremely similar and reminiscent to the one found for the cusp anomalous dimension, again, that controls these higher divergences. So it is as if we were seeing the same phenomenon as before for the higher divergences, but with new coefficients that we need to understand and with new structures that we also need to understand. So by using several techniques, we were capable of understanding the structure of this coefficient in the case of the hexagon amplitude, and we found that it's actually they can all be given in terms of a single function, which is a sort of trigonometric deformation of the cusp anomalous dimension. So you should think about taking the cusp anomalous dimension, expanding it in the coupling through arbitrarily number of loops, and then introducing some cos and sine inside the coefficient, such as to fit as a result. Okay, so in particular, the 2 extra coefficients that we found for the 6-point amplitude, and there's being some particular case of this gamma alpha that we call tilted cusp, corresponding to alpha is equal to 0 or alpha equal pi over 3. In the normalization where the gamma cusp, the original object, is coincide with a value alpha equal to pi over 4. So thanks to integrability, we can determine this gamma alpha to all loop. I mean, we have announced that, so if you want to guess, for how to deform the all loop answer that was given to us by Zertil and Stoddard many years ago, by just introducing in the infinite dimensional matrix that controls this object, some cos alpha and sin alpha here and there. Okay, so I will not spend too much time on that. It's an ansatz, but it proves to be correct through extremely, very high loop order. And we also have evidence that at strong coupling, this is the correct thing to do. Of course, there are many questions that are immediately raised by this observation, like, for instance, why does the amplitude exponentiate in the first place? Why is it quadratic in logs? And can we give some meaning to this coefficient that we have identified in terms of yet to be identified flux tubes, like it exists for the usual cusp? And for that, for this question, we don't have much to say, but there is something else we can do in order to understand better the phenomenon, which is to look at higher amplitudes, like increasing the number of gluon in the amplitude, and see, for instance, if other values of alpha are produced, if the phenomenon still persists for this higher amplitude, and so on. So one thing we can immediately see is that it is not going to be there for any type of amplitudes. In particular, if we consider amplitude with some crazy, choice of helicity for the gluon, it's not going to work. But it seems to be working for any number of gluon if we consider the simplest possible helicity configuration, which is the so-called maximal helicity violating one. And then we can immediately turn, for instance, to the 7 gluon amplitude and do some relatively quick calculation to verify that in this case as well, if we try to send cross ratio to 0, you will indeed reduce the amplitude or the log of the amplitude to something that is quadratic in log. So in the case of 7-point amplitude, we have more cross ratio. We have 7 cross ratio, which map to each other under cyclic permutation. But there is also a Graham constraint, such that in the end, only 6 of them are independent. So the best thing we can do to define an origin by sending a maximum number of cross ratio to 0 is to set 6 of them to 0. And as a result, the remaining one will be sent to 1. So the situation—
8 minutes, Benjamin.
8 minutes left?
Yes.
Okay, that will be tough. We can do that, and we can take the data that Lance and friends obtain and verify through for loops, for instance, that we have this polynomial behavior in the log up to some coefficient that we need to identify. More generally, we believe that there should exist similar limit for higher points at higher point, whenever we send a large number of cross ratio to 0, where the amplitude can be written as a sum of polynomial weighted by this gamma alpha. So the only game one has to play next is to find, those value of alpha and those polynomial, as well as those limit for which this is true. And in practice, it's very hard if you start from perturbation theory, like data at weak coupling. Of course, you can get some in from it, but we can get a different insight from string theory on how to identify angles and polynomial. So the reason why string theory is that powerful here is that, first of all, it's giving us the answer in an exponential form right away through this mapping to minimal area. And so the idea that we had was to analyze this string theory answer in some limits and try to extract the kinematical information from it and eventually dress it with proper tilted angle. So there are many simplifications here that make all of this possible. The most important one is the fact that we have integrability, and we have a solution to the calculation of scattering amplitude or minimal surfaces for any number of gluon at strong coupling through a set of TBA. And we can analyze this TBA and construct a formula. So our formula, that I will not have too much time to explain, is essentially given in the end by a convolution between an object that is purely kinematical construction that we extract directly from the minimal surface. So it's a sort of area density, which depend on a parameter here, which come from some Mellin transformation, which we convolute with this tilted angle. So the mapping with the previous variable is that Z should be seen as exponential to I alpha, where alpha is the angle. And the claim is that if you now know this string integrand, which does not depend on the coupling at all, it's just a function of the kinematics, and carry out this integral with this G that we know exactly, then you will immediately reproduce the logarithmic behavior of the amplitude. One could also carry out directly this contour integral and write the answer in a compact form as a sum of some polynomial, which again follow from string theory, and this coefficient that we conjectured. Okay, and here are the example for two simple cases, 6 and 7, with some really funny angle showing up at 7 point, but which are nonetheless in perfect agreement with perturbation theory through for loops. So things get a lot more complicated if we move to higher points. So this game of using the string integrand to write an ansatz is still doable because we have TBA for any number of gluons. So we can play this game. But what gets more complicated is that we have more cross ratios for higher point. And so we have in principle many more options in terms of how to define exactly an origin. So for the hexagon and the heptagon, there was essentially only one choice up to dihedral, cyclic group. But in the case of the octagon, we have many more dihedral classes of solution. So here is, for instance, a classification that we obtained by solving the Graham determinant constraint for 8 points, with a requirement that we have at least 9 cross ratio going to 0. And we find 9 inequivalent classes from 2 to 10, and one class of what we call super origin, which end up having 10 vanishing cross ratio. So it's not something we were expecting at the beginning that we could have such situation, but it so happened that we can also have this super origin with more than a maximal number of cross ratio going to 0. And what is more is that we found evidence through 3 loops in some situations that the double log behavior apply to all of this limit. Okay, so there is not one which is in a sense more natural to have than the other. They all happens to be supporting double logarithmic behavior. What is even more interesting is that these origins, they form webs. So it's like as if they were talking to each other or linking to each other. And the double log behavior is seen to extend now on every tile or every domain which are connecting origins with the same number of vanishing cross ratio. So here, for instance, we have on this outer domain here the origin from from 02 to 09, which all have the same number of vanishing cross ratio. And everywhere here we could verify that the double logarithmic behavior apply. So we did that by using some two-loop information, and we were also capable to construct an ansatz, which is piecewise continuous on this rosace, on this object, and which is essentially uniquely fixed. Once we know the answer at one point, we can propagate it all around the picture. Okay. We could also carry out some extra tests which are based on this Flux Tube technology, which allows us to consider higher polygon or sometimes higher loops in some situation. And in all these cases, we found perfect agreement between our general formula or template, if you want, and the information we could extract. So I would like to conclude with a more global picture that we started to dig out recently, and which is that origins are not random points. They are in fact vertices at the boundary of what is called the positive regions, of the kinematics, which admit a compactification in terms of the convex polytopes. So you should think about the interior of this ball of sorts, this convex polytope as defining the positive region, and all our origins are this asymptotic point at infinity where something interesting happens. All these vertices correspond to binary points with with cross ratios that are either 0 or 1, and so it appears natural in light of this picture to redefine or refine the definition of an origin as being essentially any vertex of the boundary, which will be characterized by the number of cross ratio being 0 or 1, with the situation being more complicated in general. You know, the higher the number of 0 we have. So the two final conjectures that we are making is that MHB amplitude admit double logarithmic behavior everywhere at every vertex of the boundary. And on top of that, we also believe that the double logarithmic behavior will extend to all faces or subfacet of this picture that will connect origin with an equal number of 0 or 1. So this is our conjecture. So of course, all of this is tested through many loops, but the entire story is very conjectural. We receive great help from perturbation theory, integrability, string theory to cook up a general formula, but it's not proven. It's not easy to prove, and it's not even clear yet that it is general enough to actually capture, all the points on this figure. So we only played with 6, 7, and 8 points, and we have no idea about how complicated the picture is getting at higher points. And there are more general questions about, why, again, I'm repeating the question I raised earlier about why do we have this exponentiation to begin with? What is the interpretation of this tilted cusp and so on? Can we identify them with some energy of flux tube? And there are also some curiosity about the resurgence of this object in other contexts, which are really intriguing. Thank you.
Thanks very much, Benjamin. And now we are open for discussion. So, are there comments or questions? I see Giancarlo Rossi.
Yes, very nice talk, though very extremely technical. Let me make just an observation from a complete outside of the field. I know of another situation in which exponentiation takes place, which is with the Bloch-Nortzik radiation from charged particle, that you can resum very nicely and get the kinematical term that kills the cross-section when the experimental resolution goes to 0. Another observation from an incompetent is as follows. There is also another example where quadratic logs appear. And this is in Parton physics, if you like, in which you have at the same time kinematical infrared singularities of various kinds, like mass and kinematical. So I don't know whether this can be any inspiration for your problem.
Yeah, I mean, it should be. It seems the way you describe it, it seems to be related to what I've mentioned at the beginning, which is the connection between, related to the infrared divergences of some observable in the theory, like the amplitude or the form factors or something like that, which are indeed controlled by this cusp anomalous dimension, which is a universal quantity that always appears. So it seems the way you describe it that it could be related to this object directly. So
also, yes, it is a universal factor. Also, the factor that controls the behavior of the cross section with the experimental resolution, because of the electromagnetic radiation that any charged particle brings in. So I don't know. It's a very important. Okay.
Thank you, Giancarlo. And Pedro, please.
Hi, Ben.
Hey.
This conjecture that you mentioned, is it true from in string theory, and that's why you conjectured it, or where does it come from, this conjecture?
Okay, so there are situations. So we have at some point, there are situations where we believe it is true. Yes, so it's just literally taking the TBA equation, going to some particular limit, okay, and calculating the resulting area. We are just writing it in some way where it becomes easier, to uplift to finite coupling. Okay, that was the idea. But there are also situations where some origin or super origin where it's not entirely clear that this is a full answer. Okay, So it seems to be the full answer at recoupling. So if we just ignore, what seems not to be working very well, and we evaluate it, and we evaluate the rest at recoupling, we get a match through a relatively high loop order. But at strong coupling, it could be that there is a departure. So it's actually not yet entirely clear, not clear yet if this formula is literally correct at strong coupling. So, and if you want an analogy, I think it's closely related to something that I think you pointed out in the paper with Frank and Till about, this this order of limit issue related to the null limit of this large change correlator, where, okay, you get a result that is true at any value of the coupling, but when you extrapolate it to strong coupling, you find that it's actually not matching the prediction that you may have in this regime.
I see.
So I suspect that something similar might be at work here, but perhaps just for some origin, not all of them. It's not entirely clear yet.
Mm-hmm. So just a naive question. So you have this shape, this positive region, and at the boundary you have these spaces, and there now you control these singularities. Let's assume it was all clean, then you could control the singularity.
Mm-hmm.
Then inside it's regular, or no? Or am I missing?
Inside it's regular, yes.
I see. So could you imagine devising some bootstrap now? Imagine you have this shape, and now you know the singularities. What would be the bootstrap? How could you imagine?
Well, I don't know if, of course, that would be great, but it's not like we it's not like we control it on every on every point on this surface. Yes, there are these vertices which are origins, and hopefully we control them here. Whenever we have two origins of the same kind which are connected to each other, we also believe we can control. But then we get some more complicated tile or facet, which are stretching between origin of different type. And there the amplitude can be relatively complicated, with polylogs, with complicated function. So it's a bit like, okay, can we reconstruct the inside if we only know the the outside, partially? So
and in the hexagon, the origin was this inner triangle becoming null. But for higher points, do all these origins have some nice geometrical meanings, or some of them are complicated?
So I think most of them are exotic. I don't know exactly what they look like. You have to. It's unclear. Yeah, you are sending some distances to zero, but then it looks. It's not very nice at the level of the polygon that you are considering. And there are some limits, like this super origin that we have for 8 point, which is kind of nice because it's related to a kind of null limit of an octagon. So, but that's the only exception, I would say, so far. The other one we don't even try to represent them. So I don't know what they look like.
Okay, thank you. Do we have any other questions or comments? Yes, I see that. Giancarlo, do you want to say?
Well, just one question. Just one question to an expert. But do we have the impression that in the large N limit, N equal 4 is integrable?
Yes.
Okay, because I was following this for a while, and then at a certain point there was a kind of controversy because this is spin chain. At a certain point they were not perfect, at very high order, were not completely fitting with the expectation.
Yeah, there was some mismatch in the past and some tensions, but to my knowledge, they were all resolved. So,
okay, so the idea is that N equal 4 at the large N infinite is an exact.
The idea is that the large N limit of N equals 4 is integrable in the large N limit, and also probably constructible in the 1 over N expansion.
Okay.
Using integrability, although it will get very complicated.
Yeah, I imagine. Sorry for retaining you.
Yeah, sure.
Any other comments, questions?
If no more physics comments, I just want to stress that there is one more day of the conference on Monday. It's not obvious from all the websites.
I was just writing that in the chat. Okay, good.
Yeah, Monday from 9 a.m. till 12:10, and the speakers will be Silvio Pufu, Kobi Sonnenschein, Gabriel Como, and then the conference ends with a discussion led by Misha Schiffman and Mithat Unsal. Just want to stress this, and also want to thank Benjamin and all the speakers today.
Thank you.
So thank you very much. And we are closing the session now, right?